So let me start here. Yeah. So actually, the idea of this is that potential energy surface is three-dimensional view, right? Now, all the times we cannot really look at the three-dimensional views and draw it properly. So therefore, we take help of contour plot of the potential energy surface. So if you look at the contour plot, perhaps we should be able to guess the or visualize the what is the shape of the potential energy surface and would be able to predict the dynamics, right? So that is basically the idea. So it's a contour line. If we have a two-dimensional function, so that means if you have a function f of x and y, right? So that is looking like this, right? Then this is like if you are looking at the three-dimensional, right, then how this function can be anticipated from a two-dimensional contour plots, right? So that is the idea of using contours in terms of the looking the potential energy surface in terms of the contours. Now look at here. This is I've just taken from the internet this picture. So this is let's say this is a hill, right? Now, if you look at this hill, this is having more steeper side, this part, right? And this is more less steeper, right? And if I project it, the same height, let's say this line, then this line, same height on a contour line, right? So that will give you the idea how this contour reflects the shape of the three-dimensional picture or multi-dimensional picture. Here it is basically 2D contour, and then we are going to the three-dimensional picture. So it's basically a function of variables, right? Now, if we connect the all the same value, same value of the function, whatever the coordinates are, right? So that gives you the contour, right? So that is the idea. Let's say I'm taking this from the bottom. This is the first line. I'm trying to get the idea of contour, how it looks like. And then if we take that line and same height, all the around the hill, and project all the points from this, what do we get? We get this outer curve, right? This one. Right? So that means it says that my base size is this, right? So you can understand from the 2D plot. So the base is going to be like that at the height, which is going to be this, right? Now, if I go to next level, this one, the second line, then again, if I project on this 2D plot, what I get this one, right? The second one, like this. If we follow all these up, now look at here, the highest point is the peak, right? So it's going to go like that. Now, so from here, what you realize is that what is going to be the shape of the 3D plot or the 3D function, right? So that is the idea of contour plot. Like looking at this, we should be able to predict what is the function. Now look at the features. Now here the contours are very closely spaced, right? So that means it gives that I'm going rising very fast. When I'm going from one contour to the other, I'm covering more slow, right? So that's why they are very closely spaced. On the other hand, if you look at this side, the contours are not that closely spaced. So if I'm going from one contour to other contour, the slope is going to be much less compared to this, right? So this contour itself gives you some idea about the 3D function, right? And okay, now let me take some other example. Like this is a coconut shell, Okay. Now I want to represent this coconut shell in terms of the contour plots. Right. Look at here. Uh, Actually, both look. If I don't put these numbers, both exactly they look like exactly similar. We really cannot understand what is the say. Right? It's like a concentric circle. Now, if I assign the value, then we should be able to say which one is the which coconut shell. Let's look at it. Like if I take this coconut shell, and if I have a instrument which I can slice this coconut shell very finely, right? The way we say when you are in hostel, if you are getting fish, we say that is fish is getting got cut by a Japanese blade, right? Something like that. If we can slice this with very fine slicing instrument, right? Then if when this face is up, right? And when you slice the top one, what we get? We get the outer circle, right? This one. And I have taken arbitrarily the value from the bottom, that let's say a height, whatever it is, the millimeter or whatever it is. So forget about the unit. So that value is 30. Okay. Now, once that is drawn, now I am going to go for again next slicing, right? Next one. So that slicing is definitely the radius of that circle is going to be smaller because I'm going from top to bottom, right? So let's say that that is value is going to be 20. So that is the second circle, right? That is the way I am trying to draw it. Okay. Now, like this, if I keep on doing slicing, then ultimately I'll go to the bottom, and the bottom one, the last one is I'm going to have, let's say value 5, whatever the unit is, and then the center is going to be here. The bottom point is going to be here, right? So if I assign this value with the height or radius, whatever you can think of, so that is from the bottom, height from the bottom of this, then you can understand that this is the outer circle is having more radius, so definitely this is going to be this one. The next one is going to be, I'm going to go down slowly, so therefore this is going to be this one, and finally I will be reaching here. So can you then anticipate from this figure with these values that this is going to be a coconut, half coconut shell which is facing upward, right? So that sorry, it got disconnected. Yeah, so that's what I was discussing. Like if you take the coconut, half coconut shell facing upward, so probably these are the contours are going to give you the idea how it looks like in 3-dimension space. Right? Yeah. Now, if I want to get a contour plot of the other half shell of the coconut, which is facing downward, then if I do follow the exactly same procedure, like slicing with a very fine instrument, then what happened now when I slice either from the bottom or the top, if I do it from the bottom, right, then the bottom circle will be of the largest radius. So that means this is going to be the circle corresponding to the bottom one slicing, right? And of course, like if I consider the height, that height will be the least height. So that's why I have given the value 5. Right? Now, if you compare with this one was bottom was this, so that was the smallest radius, right? But in this case, when it is face downward, so then the radius is going to be the biggest one, but the height is going to be least, right? So that is 5. Like this again, if I do slicing of this, then I'm going to go to get the second circle, right? And of course radius is smaller. Then doing like this, then ultimately if I go to the highest height, like that is going to be, let's say, value 30, and this point is of course going to be the center, right? I'm going to be here, right? So that gives you the idea looking at this. Now if I remove these coconut shells, and if I show you only these two contours, right, and asked you which one is going to be facing upward and which one is going to be facing downward, you can easily pointing out saying that okay, this height is higher with the largest radius, so therefore this is going to be facing upwards, and this is going to be the largest radius with the lowest height, so therefore it is definitely is going to be facing downwards. Okay. I hope this gives you some idea how really we draw the contour. Okay, now if we go for actual potential energy surface, then how we really do it. Okay, now this is the potential energy surface. We have discussed its all features, like this is going to be a diatomic potential for the BC when A is infinitely separated, right? Similarly, this is going to be the diatomic curve for the RAB, so that is product. Let me write this, then it gives you some idea. So this is reactants and this is products P, right? And if you recall this, when the reactants are basically A plus BC, right? So that is A plus BC, right? And this is going to be AB plus C. AB, the products are going to be AB plus C, right? Now here A is infinitely separated, BC is vibrating about its equilibrium distance, so that is the point reactance. So this curve is like something like it was looking like this, right? So at this point, all A, B, and C are infinitely separated. Similarly, if we look at for the AB plus C curve, so we get again the diatomic curve for the BC. My drawing is not bad. My drawing is bad, so we have to anticipate that exactly how it looked like. Okay, so this is reactants. These are reactants. These are products. Now we are going through this path from reactants to the products to this. So it should not be able to look like, and then finally coming out this side. And in between, you have the transition state. So or saddle point actually, and in the transition state theory, that is called the transition state region. Right? So that feature we should be able to find out in terms of the contour plot. Now let's say I'm exactly projected on this, right? So if you look at here, now this is going to be RAB, like this one. So that means this side, the one I have drawn it, this axis is going to be RBC, is opposite side of this, so that is coming like that, right? Then I'm plotting on this, the contour. Now let's say if we go for the height, right, the highest point on this, look at this blue curve, which is like a contour of the same height from the bottom. So that means that is having the all the points on this are having same potential energy, right? And exactly if we do the slicing in the opposite side of the where plateau is there, we get this line. So this and this are having the same potential value, right? So now if we project on this, let's say this one is going to be this, right? And then this one is going to be the outer one, this one, right? So this contour and this contour, they are having exactly the same potential values, right? Similarly, if I go for the next one, like this one, I am having same height. I am having this side also in the plateau side, right? So that is going to be the second one, and this is going to be this one. Now look at here. This repulsive surface is very steep. Therefore, two contours are very close. So that is showing that very steepness. On the other hand, this is a very flat. So this is slowly going down. So steepness is much less, right? So that gives you the idea. This is the plateau. Slowly, I'm going down, 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 and in this direction, this is going to be the minimum, right? Let's say I'm just pointing out, and then when I go up, again going up. So it is going perpendicular direction, going down, 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 again going up like this. Okay. Now, if I go this path, what it is going to look like? Let's say when I'm doing slicing, now let's do it from the bottom. If you do it from the bottom, I'm going to get a curve here like this, right? If I slice it, because I am having higher point, right? The saddle point. So I'm going to get a curve like this. So that is this one, because this point is basically the equilibrium point, right? So that's why it is giving our equilibrium, right? So this is the point, our equilibrium point is going to be the bottom of this. Now exactly similar, and if I do the same slicing here, the other side also I'm going to get the same curve, like so that is this one, right? Again, this is the point, right? So which are equilibrium of BC, and that is going to corresponding to go this one, right? So like this, if I go higher heights, I go the next contour. It is going to be this also. So that means this contour and this contour are having of the same potential. Like that, if I go further, I'm going to go up. This is higher value. So this contour and this contour is also having the same value, right? So therefore, it's going to slowly increasing the potential values. Now this is the reaction path. When you go like this, that is the reaction path, because this is reactants to the products, right? So now when I go this way, keep on slicing, I reaches a maximum point in this direction. Again, it is going down, right? So this is the maximum point in this. So this value is the bottom one. Next value is the higher value. So I'm going to do somewhere here. And then again a higher if I go this, right? Similarly, exactly same fashion, I'm going to get this side also, because they are of symmetric, because this is a thermoneutral reaction. So that means reactants and products are of same energy. So this is H plus H2, this is H2 plus H, right? So that is kind of thermoneutral reaction I am looking at, right? So therefore, whatever the value you're getting on this, you are going to get this, because they are going to be symmetrical. So now what happened, like when you go from reactant to product, look at here. So I start here, this is reactance equilibrium distance, this is going up, this value is the bottom one, then this value is increasing the contour value higher, again higher, now reaches a maximum, then when I go there, this is going to again reduce, right, reduce the value, again going down, I reach the product, and then this value this value is exactly same height. So this is actually the you can say that in case of like a transition state theory, we go like this. Here is the reactant, this is the product, this is the transition state, right? Now if we think about the potential energy surface, then when we go in this direction, this is the maximum point. Now when we go this perpendicular direction, it's going to be the minimum point, right? So this is the highest point here, then this is the lower point again below somewhere, then going down, this reaches minimum, again I am going to climb back, these two are related to this, right? So that means in this direction, this is going to be maximum, in this perpendicular direction, this is going to be minimum. So that is the saddle point we look at here, right? So I hope you got some idea how this contour plot gives you the three-dimensional view of this potential energy surface, right? Now this I have shown as I discussed with this surface itself and directly projected on this. Maybe you will get little bit better feeling if we rotate the surface along this, like this is a different plot of course, but just if I give rotate a little bit, so this rotates like that, right? So this is kind of this. Now it's exactly same reaction surface. So this is if you look at, except that this was plate 2 was here like facing us, but here plate 2 is going to be kind of 90-degree. I have rotated like this. Right. Okay. So now if I now think about this, what is my reactants and where are my reactants and where are my products? Now we are going to have A plus BC, right? So that means BC should be at the equilibrium distance. So this is BC distance. So that is equilibrium distance is somewhere, right? And AB should be high. So that means AB distance is higher. So that is my reactants are here. And this is the path, and this is basically the products zone. Okay, so that means I am here, reactants like this is the reactant zone, this is the product zone, right? Now if you look at the slicing exactly the way we have done it, then you can see that it's not exactly projected like this, but you can think about like this. If I do slicing here, right, I'm going to get a curve like this. So that is this one, right? And of course, like the same height, the other side, right? So I'm going to get a curve like this one. So that is the outermost one, right? But if you look at this value, that is not plotted in this curve because that is going out of the height, right? So this is 40, this is higher value. So this side I don't have 40, right? So therefore I'm having only this side value. Okay, now if you are going to next slicing here, so that value is 30. So that I'm going to look like this. So it is something like here, right? And then this side also at the same height, I'm going to have the 30 in this. This is going to be 30 somewhere. So this is 30 Again, the last one you can think or see, this is going to be 30. So they are going to have the same potential. So these values are in electron volts. It's already given in this. Similarly, if I keep on doing slicing, I reaches slowly this, and like this is 10. So I'm having 10 here, right? Like that. So if I keep on doing slicing, I reaches the bottom. This is this place, bottom, and this place is basically here the bottom, right? Now if we connect this slowly, I'm climbing up, because this is look at the value 0, because this is kind of 0, this is 0.3, right? So this is 0.3, this is 0 value. Let's say I'm starting with the 0. Now I'm going in this path. This is going to be 0.3. Then this is increasing. Let's say this is 0.4. Again, I'm going to go to the 0.3 and going to go to the 0, right? So that is the way we are looking at. So climbing up slowly, this is the maximum, and again going down, right? But if I go perpendicular direction in this direction, you can think of I am going, this is highest value, a higher value like 40, 30, going down, like along this direction going down. So that is 20. Then this is 10. This is 0.5. Now this value is going to be, let's say 0.4. It is in between 0.5 and 0.3. Again, when I am coming here, so that is going to be 0.3. Sorry, that is going to be 0.5. Again, this is going to be something like 1.0, and this is going to be 2.0, like this. This is 3.0, like that, and going to be going up. So that means this point, the point what we get here, I make the cross, so that is nothing but the saddle point, right? So in this direction, this is maximum, but in perpendicular direction, this is minimum. Anyway, so the idea of this contour is basically looking the two-dimensional figure, two-dimensional plot, and anticipate or visualize the three-dimensional potential energy surface, right? So that is how we go for the potential energy surface. It's going to be looking like. Now, why do we really need this? Because when we discuss the dynamics, we will project the trajectories on this contour, because surface we really cannot do it, visualize it. So we'll plot on this trajectory will be plotted on this contour plot, and we will be able to visualize the dynamics. Right. Now, this is thermoneutral reaction. Now, how it will be looking like for a let's say this is exergic reaction, right? Now here is the one reaction we have taken, which is exergic reaction, F plus H2. So this is reactants. When we go to the product, we get HF plus H. Right? Now, just by looking this potential contours, you should be able to visualize how the three-dimensional plot, three-dimensional figure look like. Right. So let's go here. So this is the reactant zone. Now, if you look at here and corresponding to this curve, so when I'm here, I'm at this point, right? Now, I'm slowly increasing the height when I go along, right? So I'm going up. So exactly I'm following this is, if I follow the reaction path, so then I'm going to climbing up. Then I'm reaches a maximum here, right, at this point. So, and that is the point here. Then slowly when I go further, now these are the downhill path, right? So I'm going to go down here like this. Now when I go there again, I go a little bit down. When I go there, I go down again. slowly like this. So I'm going to reach at this point, and then I'm at the product zone. Right. So that contour plot is going to reflect the reaction path. Is like if I do it in a plot like this. So of course, if I go from this direction to this direction, I'm climbing up. Again, this side also I'm climbing up. But look at here, these contours are very closely spaced. So therefore, this is very steep. This side, this is repulsive surface, but this side is not that much steep. And here is my plateau. Right. So that means here H, F, and H are all infinitely separated. Right. So that is the plateau. Okay. So this gives you idea about the exergic reaction. So that means if you think about kinetics, so exothermic reaction. Right. So reactants are here, products are here. I'm getting some energy out. I have written exergic because we are discussing the dynamics. Okay. So now if I go for endoergic reaction, the other way around, then it is going to be looking like this. Right. Now here, just look at this 3 dimension, then you can understand. So reactants are here. I'm at this bottom. When I'm climbing up, I'm going to a maximum. So that is the saddle point, right? Or in case of transition state theory, this is transition state. Then I'm going to go down. Now, if I plot this, how it is going to look like. Now, only thing I just draw your attention, reactants are here, not like the other page. Like, so when I'm here, I'm here, right? So these are the energy is low, right? So slowly when I'm going along the reaction path, this is I'm climbing up, I reaches the saddle point. So that is transition state. And here, so that means start here going up, like here I'm going up, it is the transition state or the saddle point, and then I'm going climbing down, but this is having higher potential than your reactants. Like products are having higher potential than reactants, so therefore this is an endoergic reaction, right? Same thing I have plotted. So I have shown this is the reaction coordinates and reaction coordinate, and if I go in a curve, how it is going to be looking like, right? So this is reactants there, this is the reactants zone, and transition state here. I'm going to go down, but these products are having higher energy compared to reactants, so this is going to be the endoergic reaction. A potential look like this. So this is potential contours, which is going to be reflecting the endoergic reaction, right? So these are the 3 type of reaction mostly we'll discuss, and complicated reaction path of course is going to be more complicated, and we'll see if we can get to those points. Okay, so I'm going to stop here, and we'll discuss further some other day.